of all, I want to thank. Okay. First of all, I want to thank you for the kind invitation and all the organizers for the kind invitation. And today I'm going to talk about the Bernstein problem for Euclidean Lipschitz surface in the sub-Finsler Eisenberg group. And this is a joint work with Manuel Ritoré. And first of all, I want to say something about the history of the Bernstein problem for the Euclidean Bernstein problem for graphs. So the problem was posed by Bernstein in 1915, and he considered an interior function U that is a C2 on the interior R2 that solved the minimal surface equation. That is that the principal curvature of the graph of U are equal to 0. The sum of the principal curvature is equal to 0. And then Bernstein, by a topological argument, was able to show that the solution is a linear function. So the graph of U is a plane. And we cannot generalize this topological argument to higher dimension. And we have to wait for Fleming in 1962. And Fleming studying the area functional and discovered a monotonicity formula, then showed that there are no trivial solutions in general Rn of the Bernstein problem. By no trivial solution, I mean hypercones. So trivial solutions are planes, and you can also have no trivial solutions that are hypercone. So if you are able to show that the no flat area minimizing there are no flat area minimizing hypercone, you are done, because you can solve the Bernstein problem, because you can show that the only solution are planes. And these give a really easy, a really simple proof of the Bernstein problem in dimension 2, because if you consider if you consider a cone in dimension 2, you have that one curvature, because the out of the singular point, the cone is folated by straight lines, so as curvature equal to 0. But you have to solve the mean curvature equation, so the sum of the two curvature has to be equal to 0. So if one curvature is equal to 0, also the other curvature has to be equal to 0. And so in this way, you can show that if you have a cone, this cone is flat. And so you can solve in this way the Bernstein problem. Later, De Giorgin and Algam show that in dimension 3 and dimension 4, there are not area minimizer hypercone. And we have to wait 1967 when Simons showed that all stable minimal cones are flat in low dimension. By low dimension, we means that n is smaller or equal than 7. And 2 years later, Bombieri, De Giorgi, and Giusti show in dimension 8 an incredible counterexample that now is called the Simon cone. That is a cone that is not flat, that is an area minimizer, and so solve the Bernstein problem. So during this talk, I will focus on dimension 2. And so this we'll talk about surface in a three-dimensional space, and we'll consider oriented surface that minimize the area functional. A natural generalization of the area functional is the Finsler area functional, where you consider a weighted area functional, weighted with this function phi, that is a function of the unit normal. So you have your surface, a two-dimensional surface, you have the unit normal, and you consider the integral of the function phi over the surface. And if you want a well-posed problem, you have to impose that phi is one homogeneous positive and C2 on the sphere, and also that the set of phi less than 1 is a strictly convex body. This is because when you compute the first Euler-Lagrange equation, so the first variation of this area functional, that is the Finsler area functional in R3, you obtain an elliptic equation. And this elliptic equation is given by the second derivative of this function phi times the second fundamental form. And S to B is equal to 0. So we have a balancing of the principal curvature. And when the function phi is indeed the Euclidean norm, and so it is equal to 1, here you obtain the mean curvature equation. So it's a natural generalization of the mean curvature equation. So the problem, the Bernstein problem for surface is a little bit different, because when you have a graph that is a solution of the minimal surface equation, you have to, by the convexity of the area functional, you have that this is a minimizer. But when you consider a surface, this is not true. And so Osserman in 1959, in the case of the Euclidean case, showed that if the Gauss map omit a neighborhood of some point, then you can give a positive answer to the Bernstein problem. This result was generalized by Jenkins in 1961 in the Finsler case, when we have this phi in the area functional, and showing that the Gauss map is quasi-conformal. In the general case of the surface in the Euclidean space, the problem was solved by Doccarmo and Peng in 1969. They consider a complete oriented minimal surface, and also has to be stable. This is important because if you want to minimize the area, you have to look also at the second variation of the area that has to be positive. And if the second variation is positive, so the surface is stable, you can solve the Bernstein problem and conclude that the only solution are planes. This result was generalized in the 80s when you consider a three-dimensional manifold that have non-negative scalar curvature. And the hypothesis of the orientability of the surface was improvement by Ross in 2006, because it showed that there are no orientable complete stable minimal surface. So now we can enter in the sub-Finsler problem, and I decided to organize this talk in 4 parts. First of all, I would like to introduce you to the new ambient space that is a three-dimensional space, that is the sub-Finsler Eisenberg group. And in this setting, I will introduce the notion of perimeter, the sub-Finsler perimeter. Then, when we have a sub-Finsler perimeter and an area functional, we can study the area stationary points of the area functional, and we can show that in this setting, the area stationary surface are foliated by straight lines. And so the equation is different, is a degenerate equation, is not elliptic, it's degenerate. And if we want to solve the Bernstein problem, we have to look for surface. Of course, we have to look at the second variation and at the notion of stability. And with the study of the second variation and of the notion of stability, we are able to give a positive answer to the Bernstein problem in this setting. So let's start. What is the first Eisenberg group? The first Eisenberg group, the underlying manifold is R3, but we consider a non-Euclidean product. That is Euclidean in the first 2 components, x and y, but in the third component is not Euclidean. So you have to sum t and bar t, but you have to add an extra term that is bar x y minus x bar y. And so a basis of left invariant vector field for this product is given by capital X, capital Y, and capital T. So if you want to be left invariant, if you want to go in the X direction, you have to add an extra term in the T direction. And if you want to, so you have partial x plus y partial t. And if you want to go in the y direction, you have to add an extra term that is minus x partial t. And when you compute the commutator of these two vector fields, you obtain the third vector field that is t, that is the partial derivative with respect to t. And now, on this space, we put the Riemannian metric that makes these three vector fields on an orthonormal basis. And we can work with the Levi-Civita connection, but for our purpose, I will prefer the pseudo-Hermitian connection. Why? Because in the Eisenberg group, we have a distribution. We can define a distribution that is generated by these two vector fields, x and y, and we cannot go in the direction of the t vector field. So we want to compute derivative that belongs to the distribution. So act only on the distribution. So we have to introduce the pseudo-Hermitian connection, that is a metric connection that is not torsion free, but the torsion of two vector field u and v is in the direction of in the t direction, and is given by 2 times the scalar product between the rotation of the first vector times the second vector v. So let me be more precise about the distribution and how we define the distribution. So we consider these two vector fields, x and y, and we generate at each point of the space the distribution that is generated by these two vector fields. So at each point of the space, we have a 2-dimensional plane in a 3-dimensional space. And of course, at the origin, this plane is the xy plane. If you look at this image here, you have the xy plane and all in the whole t-axis. But when you move the points, these planes start to rotate and changing by point. So here there is a representation of what is this distribution in all the space. You have an operator J that acts only on the distribution, that is linear and is a rotation of 90 degrees. So J of x is equal to y, and J of y is equal to minus x. You see, when you talk about sub-Riemannian geometry, you mean that you can see only a vector field that belongs to the distribution. So you cannot go in the t direction. You have to look only at vector field that belongs at these that belongs to the distribution. So we have the distribution, and we want to define a sub-Finsler norm. How we define the sub-Finsler norm? We can define the norm at the original plane, that is xy, and we fix a convex body in this plane xy. That convex body is k, is a convex body in R2 that contains the origin in the interior of k. And how we define the norm? The norm of a vector field u is given by the infimum of lambda, such that u belongs to lambda k. So we have our convex body, and we consider a dilation of this convex body such that we can reach the vector field u. So such that the vector field belongs to the dilation, and we consider the infimum. So these define a norm that is strictly convex. If we assume that the boundary of this set K is C2 and strictly convex. By strictly convex, I mean that the geodesic curvature is strictly positive. Then we have a norm, and we can define the dual norm, and we denote the dual norm by K star. And this is the supremum of the scalar product of u against each vector field that has norm k less or equal than 1. And if the norm is strictly convex, so if the convex body is strictly convex, this supremum is indeed a maximum and is reached by only one point. And we denote this point, by pk of u. By pk of u, and that is the vector that relies the supremum of the norm, of the dual norm. And this is because of the strictly convexity of the set. We have two properties of this map that is pi k. Sorry, maybe I say p, but it's pi k. This pi k is independent on the norm of the vector. So is a function that is defined on the circle on S1, and indeed is the inverse of the Gauss map of the boundary of K. So if we want to visualize this map, we can look at this image. We have the vector field, this vector field U in the circle S1. We consider the straight line in this direction, and we can consider all the orthogonal straight lines to this one, and we consider the first one that touch the boundary of K, and the point when this straight line touch the boundary, define the maps pk of U, that is this vector. This is only to visualize this map. Okay, so we have defined the norm on the xy plane, and we want to generalize the norm for all the distribution. We do that by left invariance. And if we have a vector field of component f and g, and we want to consider is k norm at a given point, by left invariant, we translate this vector field in the origin, and we compute the length of this vector in the origin. So it's really simple. And if we have a vector field, the pi k of this vector is the inverse of the Gauss map of the normalization of this vector field. In general, the dual norm is the scalar product between U and pi k of U. So if k is C2, so the boundary is C2, the Gauss map is C1, and so the inverse of the Gauss map that is pi k is C1. If along this talk, we will assume that K is C2 plus. And by C2 plus, I mean that the boundary is C2 and K is strictly convex. So K, the geodesic curvature of the boundary is greater than 0, strictly greater than 0. Okay, let's say, so this is the ambient space. How can we define the perimeter in this ambient space? And this was done by Pozzuelo and Ritoré in 2020, and by Franceschi, Monti, Righini, Sigalotti. And this is an idea of by De Giorgi, and we consider a measurable set H1, and we fix an open set omega in H1, and we say that E has locally finite K perimeter inside omega if for any relatively compact open set V, so we test we all the possible relative compact set open set that are relative compact inside omega, and we have that the supremum of the integral over E of the divergence of U, and we are considering all possible horizontal vector field, that so horizontal belongs to the distribution, are C1 and compactly support inside V. So here you see the support of U, and you are trying to define what is this boundary. So you can consider all vector field of K norm less than 1. So you are trying to test with the the characteristic function. And when this quantity, the supremum of this quantity, is less than plus infinity, you said that this is the K local perimeter. And be careful, because when E is in general a measurable set, but when E is a regular set, regular, I mean by the divergence, for the divergence theorem, you can apply the divergence theorem, and here you obtain that this is the integral over the boundary of U against the normal. And you are taking the supremum, so by this as norm less than 1, and so you can easily see that E is indeed the measure of the boundary of E when E is a regular set. But this is a generalization to measurable set. Okay, and when K is the closed unit disk center at 0, this perimeter is the classical sub-Riemannian perimeter, and will denote the unit disk center at 0 along this torque by D. So we obtain the sub-Riemannian perimeter when we fix as convex body the unit disk. Okay, so what is so now we consider a set that has Euclidean Lipschitz boundary, and we denote the boundary of E by S. If we have an Euclidean Lipschitz boundary, the perimeter K is indeed an area functional, and we denote this area functional by AK. And what is this area functional? Is the integral over the surface. We have our surface, the integral over the surface of the dual norm of the projection of the unit normal onto the distribution, integrate with respect to the Riemannian measure. So let me be more precise. We have our unit norm to our surface that is defined almost everywhere because we are considered a Lipschitz boundary. And when this normal exists, we project this normal onto the distribution because we can see only vector field that belongs to the distribution, and this is an H. And we compute the dual norm and integrate with respect to measure. And so we can, this will be denoted by NH. When NH is different from 0, I can define the horizontal unit normal, that is nu H, the normalization of this vector field. But I can define this normalization only out of the singular set. The singular set are all the points in S, such that the normal exists and the projection onto the distribution of the normal is equal to 0. So if you have that the projection of the normal is equal to 0, that means that the normal at that point coincides with the vector field T. Okay. In order to avoid the singular set, the notion of H regularity is central. So what is the H regularity that was introduced by Franchi, Serapioni, and Serra Cassano? You consider a surface, a two-dimensional surface in H1, and you say that it is H regular if locally is the level set of a function f, and the gradient, the horizontal gradient of f is continuous, and is continuous and different from 0. Okay, that means that you can define the horizontal normal nu H, that is gradient of H of f over the norm of gradient of f, and the characteristic vector is the rotation of 90 degrees of this vector field nu H, and we will denote this one by Z, and this Z is a continuous vector if the surface is H regular. So now we can understand what I mean by foliation. So we have our surface, we have the horizontal normal, and we rotate of 90-degree horizontal normal, we obtain a vector field that is Z that belongs to the surface and belongs to the distribution. So this vector field is indeed the intersection between the tangent space to our surface and the distribution. So we have this foliation when we are H regular. Franchi, Serapioni, and Saracassano in 2003 showed that the boundary of a set that has a K perimeter finite is composed by H regular surface and a singular set that has a small Hausdorff measure. Now we are ready to study the area stationary point of the area functional. What is an area stationary point? We have a Euclidean Lipschitz surface that is H regular, and we pick a vector field and the associated one parameter diffeomorph field phi s associated to the vector field S, and we compute the first variation of the area, and this first variation has to be equal to 0 for all possible vector field, and so for all possible variation. Then, with this notion, if we have our convex body K that is C2 plus and 0 that belongs to the interior of K, if S is area stationary, then the regular part of also we have Lipschitz regularity and H regular. The regular part of S is foliated by horizontal straight line. So we have our surface, and if it is area stationary, we have the surface foliated by straight lines. This result was proved by Galleri-Torre in 2015 only in the case when K is equal to the unit disk center at 0, so in the sub-Riemannian contest. And the regularity of S was C1. We improved the regularity also. Let's see an easy proof of this fact. So the proof is based on the first variation formula, of course, and by a strong regularity theory. I cannot enter in the detail of the regularity theorem, but if you have that S as prescribed K mean curvature equal to 0, by regularity theory, if you are Lipschitz, Euclidean Lipschitz, and H regular, then you can show that the characteristic curves that are the integral curve of the vector field Z are of class C2. And so you have a foliation by curves that are of class C2. A priori, our surface is only Lipschitz and H regular. So Z that is of class C1 and is a rotation of 90 degrees, that is mu H, is also C1 because we are applying a rotation that is a linear operator. Then if you have this hypothesis on Z and if you have this hypothesis on Z and mu H, you can compute the first variation formula. And what you obtain is that the first variation formula is equal to the integral of S of U against the HK curvature. What is this HK curvature? Is the scalar product between the covariant derivative nabla Z of the map PK applied to the vector field mu H against the vector field Z. So is an ODE along the curve, along the characteristic curve that are the horizontal curve that foliate our surface. In the first, what is U is the normal component of the vector field U, or the variation vector field U. And so if you look at this HK, and you, by a direct computation, you can see that this HK, so the fact that Z is C1 and nu is C1 is important, because if you want to compute the covariant derivative, you have to have that nu H is C1, P pi of K is of course C1, because we have the assumption that the convex body is C2, and so Z is also C1. and so you can compute the derivative. And the hk is equal, we can recognize that hk is equal to hd over the geodesic mean curvature of pk of nu h, and this is the sub-Riemannian mean curvature, and when we have the unit disk d, the map pi is equal to the identity, so you have the covariant derivative with respect to z of the vector field nu h against the vector field z. So if the geodesic mean curvature is strictly positive, that means that this quantity has to be equal to 0 along the characteristic curve. So that means that nu h is a constant along the characteristic curve gamma, and so the rotation of this vector field, that is z of 90 degrees, is also constant along gamma, but z is the integral, is the vector field that define the foliation. So that means that gamma are constant straight lines. Z is constant, so gamma are straight lines. Sorry. Okay, so now I would like to say some words about the sub-Riemannian Bessel problem, because it is quite different from the Euclidean one. So we fix k equal to the unit disk centered at 0, and we will talk now about the sub-Riemannian setting. In the sub-Riemannian setting, we have to distinguish between two types of graphs. T graphs, that are graphs defined on the xy plane, and intrinsic graphs, that are planes that are defined on the, for instance, xt plane. These planes are really different, because with T graph, you can have also singular point in the graph, but with the notion of intrinsic graph, you cannot have singular point. So if you consider a T graph, Cheng, Wang, Malchiodi, and Yang in 2005, and then Ritoré, Rosale refined the result, show that a C2 minimal T graph is congruent to an hyperboloid or an Euclidean plane. So we have that the Bessel problem is quite different, because the solution are not only Euclidean plane, but also there is also the solution of a hyperboloid. And you can ask, can I consider low regularity? No, because Ritoré in 2009 showed that there are several examples of Euclidean Lipschitz T graph that are area minimizing. So if you enlarge a little bit the class of minimal graph, lowering the regularity, you obtain a lot of examples that are not Euclidean planes and that are not the hyperboloid. The problem is that you cannot control the singular set if you have low regularity. With the C2 regularity, you can control indeed the singular set. And Hurtado, Ritoré, Rosales in 2010 showed that if you have a C2 complete orientable, stable, and connect surface, then you can conclude, you have to add the stability condition. You can conclude that the solution are Euclidean planes or the hyperboloid, are congruent to the hyperboloid. So this is the case of T graph. Let's have a look at the case of the intrinsic graph. An intrinsic graph is a function on the xt plane, and so you have a graph on the xt plane, and Danielli, Garofalo, and Now in 2008 show a family of graphs that is U alpha that are C infinity, and that are area stationary, so solve the equation the equation, but are unstable. So they are not area minimizing. After that, so this is completely different. The nature of the Bernstein problem for intrinsic graph is completely different, because in Euclidean case, you have that you solve the equation, and automatically by the convexity of the area functional, you have that you are a minimizer. In this case, it's not true, because the area functional for intrinsic graph is not convex. After that, Monti, Saracassano, and Vittone in 2008 show that an area minimizing intrinsic graph of low regularity, that is order continuous 1/2, is an intrinsic cone. So you in dimension, if you lower the regularity, you have that the solution are intrinsic cone. So we have seen that in dimension 8 in the Euclidean case, but in this case, with low regularity order 1/2, you have area minimizing intrinsic cone. After that, Galle and Rittore in 2015 show that a complete orientable stable surface that is C1 and has a singular set empty is a vertical plane. And after that, Nicolussi, Golo, and Saracassano show that under the Euclidean Lipschitz regularity, a stable area minimizing a stable area stationary intrinsic graph are vertical planes. So so also for graph we have to assume the stability, of course. And we want to improve these two results and generalize to the sub-Finsler contest. So if you want to do that, we have to look at the second variation and the stability. So if we look at the second variation, we have the second derivative of the area functional, and the second derivative of the area functional is the integral over the surface S, such that Z of u square plus QU square multiplied for this factor is greater than 0. This is the stability condition. So these are the derivative only in the direction of the characteristic curve. And we have also this function in front of the u square. U is the normal component of the variational vector field. And the function Q is given by this function where we have the derivative of n against the vector field t over the norm of nh minus the square of this function. And the problem is I assume that my surface is a priori Euclidean Lipschitz and H regular. But so I don't know if this function is differentiable in the z direction. And so I have to be careful. If I want to look at the stability, I have to prove that this function is smooth in the z direction. Let's see this result. And to obtain this result, we use a Codazzi type equation, and this theory was developed by Cheng, Wang, and Malchiodi. And the idea was to recognize that the function f, that is now the n against the vector field t over the norm of mu h, satisfy a differential equation along the horizontal curve that are the characteristic curve. And this equation is the Codazzi equation along the straight line. And if you prove that you solve this equation, then automatically by bootstrap, the solution has to be smooth along the straight line. First of all, we need a lemma, a simple lemma of ODE, that the only solution of this equation, if we fix an initial data at the time 0 equal to A and a velocity equal to B, is given by this rational function that is a ratio between a one order polynomial in the numerator and a second order polynomial in the denominator. And this solution, if is defined for every S, we have a duality. Either A square minus B is strictly greater than 0, or the function, the solution, the only solution is the trivial one. So we have this duality that play a really important role in the proof of the Bernstein theorem. Also, this equation solve another equation that f squared minus f, the first derivative, satisfied this equality. But this is not really important. But we will use that later. So, okay, so let's try to give a proof of these things. We have we can parameterize our surface in a little neighborhood by a Lipschitz function that is defined by the function u that defined on D, and this is an intrinsic graph because we can go in the y direction because we have a domain on the xt plane. And we can go in the y direction, but if you want to go in the y direction, we has to go also in the t direction, so u appears also in the third term. And if we assume that S is stationary, then in this case, the nu h, the unit normal, is given by this vector field that depends only on this function that is ux plus 2 times u ut. The partial derivative that is constant along gamma. So this function b, I will call this function b, is constant along gamma. That gamma is the characteristic curve. Because we are stationary, we have proved that a stationary surface is foliated by a straight line, and so we can consider a parameterization of a curve on the domain D, and that is STS, and we can lift this little gamma to a general curve of S that is capital gamma. And if we compute the derivative, we see that we have an extra term in the third component. So if we want to be horizontal, the terms in the third component has to be equal to 0. So horizontal curves have to solve the differential equation, the OD t prime equal to 2 times u. So u now is an Euclidean Lipschitz function. So I can solve the Cauchy problem. I fix a small parameter epsilon that will be the initial data of our Cauchy problem, and I consider t prime epsilon equal to 2 times u along the curve. And the Euclidean Lipschitz regularity ensure that we have a solution, and we can prove that this define a B-Lipschitz homomorphism that will give us a change of variables really useful in this constant, and this change of variable we call by G. If we compute now the second derivative with respect to S of T epsilon, we have that this second derivative, we have to apply the chain rule, so ux times 1 plus ut times the first derivative of t epsilon that satisfy the equation. So this is indeed equal to the constant b I defined before, this one that was constant. So this is constant for each epsilon fixed, and so by the Taylor expansion, we can write t epsilon that depend on S, that is a polynomial of second order, where A is 2 times U at the time 0, comma epsilon, because when we evaluate in 0, we have this function A. So now, a priori, this T epsilon is only C11, is not C2. So I cannot apply the Cauchy-Schwarz theorem that the cross derivatives are equal. But in the distributional sense, for almost every epsilon, because in S we are smooth, but in epsilon we are not smooth, we are only C11. So the second cross derivative has to be equal almost everywhere, not at each point. And if we have this equality almost everywhere, that means that on the left-hand side, we have to compute T prime epsilon, and we have to consider the derivative with respect to epsilon of T prime epsilon. But if we have a look of T prime epsilon, we have to derive this quantity with respect to, we have to differentiate this quantity with respect to epsilon. So we have the only derivative with respect to the second term times T, the partial derivative with respect to epsilon of T epsilon. And so this is exactly what we obtain, because this is ut evaluated along the characteristic curve, multiplied for the first derivative with respect to epsilon, T epsilon. If you remember, this was epsilon plus A epsilon S, so we are taking the derivative with respect to epsilon. And on the other side of the equality, we have to consider the first derivative with respect to epsilon, that is simply the derivative with respect to epsilon, and then we have to compute the derivative with respect to S, so we obtain this factor. And so what we obtain that ut, the partial derivative with respect to t, is as this representation, so that is the relation between one order polynomial over a two order polynomial. So if you remember, we had a lemma that said that this was more or less the only solution of an ODE. And so we have to reparameterize a little bit the curve, so we have to consider gamma minus S, but if you reparameterize a little bit the curve, we recognize that n against t over the norm of mu h is indeed ut over this quantity, and this quantity over this quantity, and this function solve the ordinary differential equation along the curve for almost every epsilon. So we have with initial data a prime epsilon over 2 and velocity a prime epsilon square over 2 minus b epsilon. But the important thing is that solve the Codazzi equation, and so is smooth. So I can compute the second variation, and now I'm able to show the Bernstein problem. If I have time, I will be quick. Okay, so we have a surface that is complete, orientable, stable, and we have the Euclidean Lipschitz regularity and H regularity of the surface. Then we can prove that S is a vertical plane. So if you remember the parameterization given by T epsilon S in the proof of the proposition, we have that by the Oprinoff theorem, if S is complete, we can extend the set where the function T epsilon is defined to the whole R. So we can extend the geodesic to the whole R. And we have to look at the stability condition. So S is stable, we look at the stability in the chart G, that is defined by the T epsilon S. And we obtain this quantity. We can recognize that this quantity, if they solve the OD, so these can be written in with respect B prime and A prime in a standard way, and also the Jacobian of the transformation can be written with respect A prime epsilon and B prime epsilon. So we obtain that the second variation, the stability condition, can be written with respect I prime and B prime, and for all possible f that are differentiable in the s direction and continuous. But now we want to concentrate the stability condition on the straight line. And so to concentrate the stability condition, we have to consider a specific test function that is the product between a function, a test function phi with the parameter s, and a bump function with respect to the parameter epsilon. This bump function converges to a delta of Dirac, and so we can localize along the straight line the second variation, the stability condition, and what we obtain is this inequality, but where the integral now is only over R. And this can be done because K is strictly positive and is also a constant, and also this term that appear here is a constant, and this can be done because the convex set is strictly convex. And we recognize, if we call a capital A minus I prime and B, a capital B, 2B prime, and HS, this polynomial that appears here and also here, we have this formula that the second variation is indeed given by this formula. And now we can apply a lemma, a technical lemma by Barone, Adesi, and Serra Cassano, Barone, Adesi, Serra Cassano, and Vittone. And so if we assume that the quantity, this quantity in front of this term is positive, then by the theorem by Adesi, Serra Cassano, and Vittone, we conclude that this 2b has to be equal to a square, and so we have the 4b prime is equal to a prime. But if you remember, in the ODE lemma, we said that if that we had a duality, or sorry, this is the technical lemma, or a square minus b, now a and b are different, is greater than 0, or the solution is the trivial function. So in this case, we can apply the ODE lemma to conclude that the function is the trivial function, and so I prime epsilon is equal to I prime epsilon is equal to 0. And in the other case, when 2b minus a square is less than 0, strictly less than 0, then we directly have the inequality of the lemma, the converse inequality. So by the lemma, we can conclude that the solution is only the trivial one, and so the first derivative of a and b is equal to 0, but a and b are Lipschitz function whose derivative is almost everywhere equal to 0. That means that they are constant function, and so we can write T epsilon s with epsilon plus as plus bs squared, where a and b are two constant. So the first derivative of T epsilon is a plus 2bs, and this by the how we define T epsilon is equal to the function u in this new chart, and this means that u is an affine function, and we are done because we have solved the Bernstein problem. Thank you very much for the attention.